How do you see the text? Oh, I think then we should also open that page. We should have a link which I posted. But it's also there on this, in the Creator Studio. Yeah, edit. Yeah, I just go and also share on like. So this question mark here. Where is the link? View and watch page. View is this. I'm getting no. Yeah, the view. No, yes. Just erase it, it's circulate. I think we can reduce the resolution also. Take too much of the bandwidth. People are dead, I think. You just start talking and ask them if they. So that is not. That's just the feedback that we get. I don't want feedback. Like mute is just. They can hear. Hello, are you able to listen? Hello. So, okay, we'll wait for a couple of minutes to see if few more people join. And what you could do is try and type down your questions, and we will try to answer as many as we could. So we'll have this session for about 40-45 minutes. And we could also have it a little more regularly if many of you desire. So I hope the audio is clear and the video is also clear. There's a bit of lag, but okay, we'll try to live with that. So, I think we start asking their questions. Okay, so I'm having a bad throat, so my apologies for that. We start with the first question asked by Anvesha, and the question reads, what is the importance of impulse response when we generally analyze the step response of the system? Uh, so the reason why we do this kind of response testing, or we see how the system responds to an impulse or a step, is essentially to look at what. So a step is a signal where you can just check if the system is possibly naturally stable, right, or how the system reacts to sudden disturbances. So, as an example, say if I take a normal pendulum, say just this way, and if I just if I just give it a little push, this is something which is like an impulse, right? So, because this downward position is stable, you see that it actually retains its original configuration, right? Similarly, if I look at this one, and the inverted position of a pendulum, if I just give it a little push, you just see it actually come down, right? So this is some kind of an unstable dynamics, that if I take an inverted pendulum, I supply a little impulse, it turns unstable. So one definition of stability, or one way to interpret stability, is also via its impulse response. So the idea of impulse response is to look at system in terms of how does there is a certain disturbance in the system. Step response is of course, because in most cases we just many cases we just switch on control, and the control just goes on, right, for almost like forever. So that is like what we call as the step response. But so each one has got their own importance of why do we analyze why do we analyze systems with respect to particular test signals, like the response, step. We also look at a ramp input and so on. So, and the reason, I think it's also in the lectures which is told, is that the reason we just stick to these 2 or 3 basic signals is all the other signals are in some sense a combination of a step, impulse, or a ramp, and so on. Right. So I think that's more or less the reason why we do testing with different kind of signals, and each has its own interpretation. Step signal is stable or unstable? Well, it's just a signal, right? So I would not really look at it in terms of stable or unstable, right? If you look at a ramp, it actually also goes to infinity as t goes to infinity, but we not really categorize signals as being stable at the moment. Well, I think that's not a right way here to look at it at the moment. Okay, so there are some. Pranav says, please give some practical examples of various standard signals. Like I gave one of the pendulum, right? And others could be, say, for example, if say look at in terms of a disturbance, right? So if I say I am going horizontally on a car, and then I just have to climb up, let's say an inclination of say 10 or 15 degrees, right? So that is kind of a disturbance which is like at a constant angle. Right? So what we see here is that this can be modeled again as not as a step disturbance, where the disturbance comes and stays, but it's kind of constantly, the slope here is like a constant, and then you have to really look at your design parameters of how this is, how the system is responding to this kind of disturbances. And say, for example, take also a room with air conditioner, right? And then if you see that constantly people are walking in, walking out, so all of a sudden just 10 people enter, that could be an impulse. People are just constantly walking in at a constant rate, like one person is just coming in every minute. That's like a step, and if you see that the people are just increasing over time, that's kind of a ramp input. So the examples of these are like several, right? So of some standard practical examples. So There's nothing really. So I think most systems which you encounter are actually in. If you look at disturbance rejection of most systems, it is it will definitely be like one of these things. So there's a question of steady state error for non-unity feedback. Okay, so let's just talk about what is the error. In a typical configuration, what we have is a reference input and you have the measured output. Okay, so the difference is always between the reference which is set, like say 25 degrees for a room, and the output. So if it's a non-unity feedback, I will not really worry about of it being a unity feedback or a non-unity feedback, as long as my definition says that it is a difference between the reference and the actual value. In the unity feedback, it just turns out that it is just a difference over the summing block, but that's not a general way. For non-unity, I just look at the difference here and the difference here.
The formula will not coordinate equally.
Yeah, okay. Also, what Jaydev just added is that those formulas for steady state error are also for unity feedback. However, what we know is, given a non-unity feedback system, how do we connect it to a unity feedback system? So you can write it down as a unity feedback system and then do all the steady state error analysis. But for simplification process, we just look at a unity feedback system. But going by definition, the error is between the reference and the actual value. So there's a question which asks why flux remained constant in core for no load, full load, half load. I don't really understand what kind of flux you're talking about here. To me, it seems something like a question from machines. Could be a transformer or maybe even some kind of a motoring action. So I think you may have to be a little specific in asking questions. Also remind yourself that we are here not doing a machines class, but a controls class. So if you can formulate, I can try to answer the question related to the flux. Hi sir, my question is, LTI systems are existing in practical or not? If yes, give examples. I think most systems, what we do, right? Even if you look at, so first, I think we'll just quickly revisit what does it mean by LTI system. So, sorry. So when I'm talking of time invariance, I'm essentially talking about the properties of the system or the parameters of the system, like mass or in some cases frictional constant. So take any robotic example or a robotic arm or a planar manipulator. All these are essentially time invariant systems. We could argue that, well, the mass might change eventually, but in the time scales which we are operating, say for example, I am doing an experiment and I'll be interested in doing the experiment over the next 2 or 3 months. I will not expect the mass to change drastically, right? So all we do is we look at the time scales that we are operating, and in the time scales that we are operating at the lab level, we can consider, for example, a robotic manipulator as a time invariant system. It depends on how complex you want to model that. Whereas if I were to look at a fighter aircraft or even the standard passenger aircraft, you see that as the aircraft keeps moving, the mass decreases as the aircraft keeps on burning fuel. Again, these kind of examples are almost everywhere. So I can show you my fan here. This is an LTI system, right? On the top. Actually, all you learned in machines course was to model an induction motor. It's essentially an LTI model. There's another question by. I was not seeing that. Okay, so in other question, it says, does signal contain information? Again, want you to be a little more specific in asking this question. I mean, I don't really understand what does it mean by signal containing information. Of course, signal does contain information, but what are the things that we are trying to do here, or in what context are we looking at this information? If you can be specific on that, I can answer. Okay, so Lokesh has this interesting question. It says, the author said natural response is the transient response and the forced response is the steady state response. But you have said that natural response is zero input, forced response is steady state response. I think this is kind of opposite. I think there have been several questions also on the forum. Say, for example, look at again. I'll just take this simple example and just take the pendulum. If you just perturb, its natural response will be to come back to its initial position. You know, the transients and all will die out. So, say on the other hand, say for example, at this hinge, I just put up some kind of a spring action. So what happens is that, well, after the transients die down, the pendulum is now is resting at an angle of say 30 degrees or whatever. I think so natural response is, so the transients are essentially decided by what is the natural response of the system in terms of its damping coefficient or even its natural frequency or even the damped frequency. Force response is what remains after all the steady state things are gone. For example, if I just were to switch on a spring over here, it might take some oscillations before it settles down to this position, right? Or even a fan, right? If you just switch on, it doesn't really attain the steady state speed instantaneously. It has some transients based on the properties of the system, and what remains when you see the fan is after a minute or so is its steady state response, and that essentially is the forced response of the system. So it's, I think they mean like one and the same. So Shweta asks, I don't understand the spelling, but where do we see this kind of this type of fictional example? Okay, so if you are asking in a question in continuation of what I'm saying, I think you may refer to that question because of this time lag. I think it gets a little mixed up. What is the importance of zeros for stability? Well, stability essentially depends only on the pole locations. Zeros, however, play a very important role in terms of system being faster in response, slower in response, and several other things. So if you could hold on for a while, so we have a complete module where or a set of lectures where we dedicate ourselves to handling zeros. That comes in maybe module 10, especially where 10 where we talk of non-minimum phase zeros, and also a bit in module 7 when we actually see the response of adding zeros. That will be when we will do the PID based, not design, but when we learn the PID based concepts. Sorry. Okay, so I will not answer transformer related questions at the moment. I will keep that to later. Right? We'll answer control related courses. How do we design a summing block? Is it a difference amplifier? Well, I'm not sure if that could be the only way.
It can be a difference amplifier, but many other ways. It
could be, but there are other simpler ways. But we just assume that there is somebody who just gives us the summing block. Right? Not really worrying about the design. Yeah. So the design possibly we will outsource that to instrumentation guys. So what we will be interested here is like, okay, there is a summing block. I can do certain things with that. Now I'll ask myself a question: what all I can do after I have a good summing block. Okay, so does signal contain information? Well, again, I think of the idea of signal containing information is again, what do we want to call as input? So if I take a signal as my reference signal has the information that, well, this is what my actual system should behave in terms of speed of the car, temperature of the air conditioner, and so on. Any other information, I do not know what is actually meant by information here. Okay, so the next question is how to analyze a third order system in the time domain analysis. Is it right to split it? Well, I think you could actually do that, split it into a first order system and a second order system. You could try doing that and add up, but okay, I would not really have a definite closed form expression answer for that, but we could actually try that. Or and so a bit of this we'll also talk of a little later, where we can actually make it an approximation of a second order system, right, when we talk of dominant poles and so on. So you can actually try doing that, split it into two systems, and then look at it as into G1 and G2, and then you look at the overall response as maybe G1 plus G2. A bit of this we'll do maybe during, again, when we talk of responses of the system, right? When we talk of dominant pole analysis, while we do the design section. Okay, so the zeros is coming very soon, right? Maybe in a couple of weeks. At least a good section of the importance of zeros will come up in a couple of weeks. Why only absolute and relative stability of non-minimum? Okay, even the Bode thing, I think we'll wait because the question on the Bode plot may, so people who are doing this course for the first time, they may not be able to relate that, but we will do a lot of non-minimum phase analysis of the Bode plot in the coming lectures. So okay, so I think we'll skip this because this requires a little more explanation of the understanding of non-minimum phase systems, and we have a complete module which is actually dedicated towards a non-minimum phase behavior in systems. In the root locus, is it possible to have more number of poles than zeros? So Madan Rai asked this question. I wouldn't know what it means, but we usually strictly proper transfer function will actually have more number of poles than zeros. If you are asking the other way, could there be more number of zeros? The answer is no. And we have been, I think, talking of those exists of a strictly proper transfer function. We also talk about it a little later when we do the derivative composition, which actually, in an ideal case, is a system which has 1, 0, and no pole. We'll see why those things are not physically realizable. It's essentially some kind of non-causal system. So we would here eliminate non-causality. Solve the question of non-unity. Okay, Raj says to solve the question of a non-unity feedback by converting to unity feedback or any method, in automatic control systems by PC code gives another method. Both answers are different. Okay, first is you need to ask yourself what is the question that we are trying. Okay, sorry for interruption. So, does converting a non-unity feedback system to a unity feedback system give me the same answer? Well, I think it depends on what is the problem that you are trying to solve. If you can show me an example where answers are different, I would be interested in looking at that. But the transfer function will actually be the same in both cases. Yeah, you can post actually the specific question in the forum, right, with the two different answers. Sorry. Okay, I'll skip a bit of this question on the initial conditions, right? I think if we go back to what we are doing in Laplace transforms, they might be a little more obvious. That question is almost like answered over there. Okay. Then next is, what is the steady state error in a marginally stable system? Well, we wouldn't have a notion of a steady state error over there because your system might, if we're just talking about second order system, you just have sustained oscillations. So we will not talk of a steady state error over there. Can I say open loop system is unstable always? No. I mean, there are ways to say to detect when system is stable or not. It has actually to do with the impulse response or even the poles of the system. You want to answer this question?
Okay, the question is, while taking Laplace transform, we say all initial conditions remain stable. What do we mean by that? Okay, so this is some sort of, so when we are talking of applying a control input, so we are assuming that there is some kind of switching that is happening. So when we are applying a control input, we kind of apply it as a switch. So the conditions of the system before applying that switch are assumed to be in a steady state or zero initial condition. So it has no prior response or prior transients existing. So it's in a kind of steady state at that time. And so once we apply the switch, so we can assume that there are no initial conditions or the system is in a steady state. So that's what we mean when we say that the initial conditions are zero while taking a Laplace transform.
Okay, that's good. So another question says, if the open loop system is stable, does it imply that the closed loop system is always stable? Okay. It can. All combinations are possible. Open loop being stable, the closed loop can become unstable.
Depends on the field.
It really depends on lots of things. I think we will talk of this. Maybe you look at Nyquist actually gives you some answers about this. Right? That if the open loop system is unstable, there are we can make the closed loop system stable, and then there are ways to check of the closed loop system stability. But there is no one answer to this of can something be something else? Well, all possibilities are, or all options are possible. What do you mean by open loop transfer function GH? Can we call it open loop? Yeah, we just call it. I think that's just the terminology we use. Some books also call it as the loop transfer function, but that actually helps us in a bit of an analysis, because if you look at most of the analysis here, including your steady state errors or what we do even in Nyquist or Bode, are essentially, or even root locus, that just give me the open loop transfer functions G or H, and I can tell you the closed loop behavior. So a lot of this course is essentially understanding the closed loop behavior by just looking at the open loop transfer functions. Again, there's a question, sir, why mostly open loop system is stable than closed loop? Okay, so there are lots of open loop control systems which are stable, and then we can do a bunch of. There are all, I think, again, here all kinds of things are possible. Okay, there's something of the type and order of the system, I think. Okay, there's just with definitions, right? So the way we call here is the type is the number of poles at the origin, again, of G times H. Order is, again, it's a little different meaning about how many poles the system. Saurabh Vivek Vajekar asks a question, sir, how can we make a nonlinear system linear for the penals? So the linearization of nonlinear systems we will deal exclusively while we are doing state space analysis. So just to give you a little hint, we just use the what is called as the Jacobi linearization, or also what is in a way like a Taylor series expansion kind of phenomena. So we will do that while we are doing state space analysis, and we'll do a bunch of examples related to that. Also see what is the information that is lost when we do this linearization, what is the useful information. Okay, so Ishwar asks the question, how do these system identification techniques control or translate to the empirical world? Do we use same tuning techniques? For example, conical tag. Okay, so I do not remember by heart what you mean by a nonlinear conical tag, but I do not know what is even the empirical world. But one thing which I could say is,
I think he's talking of empirical system identification versus law-based, physical laws-based system identification.
okay. So if
Like experimental basis.
so, okay, so there are. I'll answer a little differently also, right? Of what are several modeling procedures. The first is if I give you a circuit, you can actually write down equations for that, or even any mechanical kind of system, right? Because we know what are the governing laws in terms of Newton's laws or Kirchhoff's laws or the energy conservation laws and so on. So that is not an identification technique, but that is something which we can model directly. Now, what is the empirical thing to do is, for example, if I cannot write down physical laws, or for example, if I do not know what is intense system, which is like what they call also as a black box. Under that conditions, what I would do is send in or give the system some standard test signals. And okay, there is a big research area where it essentially deals with system identification, but essentially we look at input, give some input signals and check how the system behaves at its output, and then identify the transfer function or its properties. One easier method or one straightforward method which we will also learn eventually is to draw the Bode plot of the system. Right? I can subject my system to several frequencies ranging from say 1 hertz till some 10 kilohertz or even megahertz in that range, and I can just observe the response of the system and construct a Bode plot. So once I have a Bode plot, I know how my transfer function would look like. So you get a good feel of these things, right? When we do the Bode plot, and then there are several advances in those techniques also. The nonlinear tank, I think in that case there are no physical laws which will tell us the relation. I think it's to do with the discharge rate and all. And that model essentially is a result of empirical or a result of lots of experiments. And I think that's a very standard example which every system identification course also uses, or any process control textbook also uses.
How do you control this empirical
Uh,
Can I control the system?
So, okay, what is the control thing here? Okay, so there are two separate things here, right? So one is the modeling part, other is the control part, and both are like, okay, they do exist together. But whenever I am doing my control synthesis or control analysis, I assume that the model is there. Which means there is some guy sitting out there who is doing for me all the experiments and giving me the model, and I will just be interested in that model. Okay, how can I stable and unstable equilibrium point? Well, there are a bunch of ways, and I think we will. So, for example, a good thing to look at is from the Nyquist point of view, where if I have an open loop unstable system, which means there is an unstable equilibrium point, I could make it closed loop stable. There are a bunch of design methods, which I think is this forum might be very short to talk of that, but there are several methods where I can actually stabilize an unstable equilibrium point. Just like take the pendulum example, right? I can always stabilize the pendulum to this angle by proper, proper control laws. Right? We just put a spring which will hold it here in this position. It's not as straightforward as that, but there are several techniques to do that. Arnav Day asks the question: what happens when a system will be marginally stable? What do you mean in terms of what happens? It's marginally stable. It's just marginally stable. It just keeps oscillating around the reference point or the equilibrium point. Sir, are inductors, capacitors are linear devices? Well, they are not. I think when you look at the your standard text in electromagnetics, what you read are they are essentially non-linear, but for our range of operation, we safely assume them to be linear. And there's another question: what to do with unstable system in open loop? Okay, I think I've answered that question already in a different way. Karthik Raja says, I have asked a question in discussion forum in week 1. Please. Okay, I'll look at that. If So Karthik Raja, we will try to answer your question. By gain margin and phase margin methods in the body plots, we find relative stability of closed loop. Or okay, so okay, again, listen to this very carefully here, right? So are the gain margin and phase margin. So this essentially will tell me, because whenever I'm even drawing the bode or the Nyquist or even the root locus, what does the plot tell me? The plot in the, say take the root locus, right? In the root locus, the plot will tell me how my roots are moving as the gain k increases. Roots of what? So these are essentially the roots of the closed loop system. So if I say my system is stable for gains between 0 and 100, that essentially is for the closed loop system. So just again look at it, all these things carefully, right? Even the definition of gain margin or phase margin, look at the Nyquist plot. It comes as a result of drawing the plot for 1 plus GH. And then you look at encirclements about the origin and then translate it to this point minus 1 plus J0. So once I translate it to this point minus 1 plus J0, what I can do is I don't really need to look at how the closed loop system looks like. I can translate everything to G times H with reference to the point minus 1 plus J0. So here again, closed loop behavior, or closed loop information we are getting via the open loop. We're just analyzing the open loop transfer function or the loop transfer function G times H. Whether all third order systems are unstable in open loop? Well, I think the answer is no. If you ask all, the answer is no. Of course, we'll deal with a bit of third order systems and look at some peculiar behavior of that while we are doing this P, I, and D component analysis. Okay, are raw stability and Hertz criterion different? I think towards the end of our lectures, we have a little story on how this Routh and Hurwitz parallelly worked on this stability theory and came up with a nice looking technique. I think these are essentially the same, and therefore it is named as Routh-Hurwitz. You may want to just go through the story which was told towards the end of the lectures. I think it's in one of the slides. Okay, I think if there are no more questions, if you have any suggestions in general related to the nature of problems we do in the slides or tutorials, or the nature of assignments, are they too easy, too tough, difficulties with the forum, those things also you could share over here. Is there? Okay, I think I'll can just post this in the forum. I can post some nice material on this nature of damping. What could possibly mean by negative damping? I'll just post something if you sort of ask this question on the forum. Maybe I can have a little detailed answer also of that. Okay, any more questions? And it'll also be nice if you could tell us if you need these forums a little more frequently, or assuming they are useful. So we could do it like maybe once in 2 weeks or once in 10 days or anything like that. Can we find stability? Okay, see, I think the way we should look at things here is take a system, positive feedback or a negative feedback, and just relate the definition of stability. Does not say that blah 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 is the definition of stability for negative feedback system. Right? The definition still remains the same. So either a positive feedback, negative feedback, open loop, closed loop, third order, the definition is always the same. So you can look back to the definitions and try to answer your question, and the answers then kind of will become very, very simple. Difficulties. How to find relative stability using RH criteria?
Shifting up.
Well, I think one thing what we could do in Routh Hurwitz is, I think in some of the problems we so the standard definition of stability says or relates to the poles being to the left half plane. If I say, well, my system, I want it to be relatively more stable, means I want to push my poles a little further away from the origin. So I could pose my problem in the following way. Does my system have all the closed loop poles to the left of -1? And I just do the simple coordinate transformation, right, of just changing the origin from 0, 0 to -1, 0. That is one relative stability analysis which we could do with the RS criteria. On the other hand, if there is an unknown parameter in the system, say some number m or a k, I could draw the root table and then just find out under what values of k there are no sign changes. So, but then these are not really useful or informative in a big way, and therefore we have the root locus criteria. Effect of feedback on sensitivity. I think I'll post some notes on this, right? Because it's again we have to start with the definition of stability, and then I think it should be there in one of the slides. If you could ask me a specific question, Shweta, I can answer you this. But the effects have already been discussed in the slide. Vinayak Shinde asked a question: in Routh stability analysis, we find two difficulties to continue the further analysis. This is what are those two difficulties, and why does
0 in the column and 1 0 in the first column?
No, it doesn't mean the system is unstable, right? So we have ways to overcome those. I mean, assuming I understand your two difficulties well, then there are ways to circumvent those difficulties. I think you'll see those difficulties even when we do the Nyquist contour. But it doesn't say anything about stability, right? So if there's a 0 or if it's epsilon is 0, the system could still be stable, it will also be unstable. I mean, all possibilities are there. Okay, why do we mostly have negative feedback in control system? Okay, look at this thing, right? Again, I want a reference speed and a desired speed, right? And what does the negative feedback tells me? That I am either so if the reference is 45 kilometers an hour, I am at 40. It will say, look, the error is 5, and then please go pump in your accelerator a little more so that you go at 45. Similarly with the air conditioner, right? Any reference tracking naturally is a negative feedback system. Look at it more from the practical point of view. Forget the math for the moment, but we are actually comparing two values, right? If this is the reference, this is here, so I may have to pump in a little more energy to reach this point. Please suggest more books. I think books are there everywhere. There are, I think, tons of material even available on the web. So I would say just grab any book and just problems and keep solving. And there are also, I think, some textbooks posted on the forum. I think the material today is available in plenty on the web. You can just look at any of those material. Any formula for sensitivity of feedback? I think Shweta, if you could post this in the forum, I can actually guide you to the right slide. I don't by heart, remember the number of the slide or the module, but I think there is a very direct effect which I think it's already been answered. If you just post this, I will direct you to the right slide, because at the moment I don't remember the exact place where it is in the lecture notes. Well, again, positive feedback systems could be all everything. It could be stable, unstable, marginally stable. Again, asking the question, ask in terms of definition. right? A positive feedback system can actually be stable if the definition of stability holds, or the conditions to check stability hold, right? So it's all combinations are still possible. Which is the best book for Git? Again, the answer is the same, right? So you just get any book, any material on the web and start. I think there are tons of them available online already. What I would, however, like to say here is, if you pinpoint certain problems which you have difficulty in solving, then we could help you solve those problems. Okay, what is saturation? Well, I think it's. I think we have come across this terminology in several courses already, right? So maybe an input saturation could be if I'm just increasing my input and it just cannot go further than a given threshold. Then I think I can say that my system is saturated. It just depends on what kind of saturation you are looking at. But the definition again is standard, right? Also, with the necessary meaning, it should be obvious what is saturation trying to tell us. What is the final value theorem? Well, I think. Yeah, so final value theorem is only for stable systems. So first we should make sure that the system is stable before we try to do anything. I think I think the proof is also kind of quite straightforward, which you would learn in any single course. So what here is important is that before I apply the final value theorem, I should check if the system is stable or not. I think this question on root locus I have already answered. So just go back to those answers.
Somebody asked why system is stable and roots are in the right half of the screen. It's not stable.
Very nice. There's a question. Why I missed this? Vaishnavi asked the question: why system is stable when roots are in the right half of the S plane? No, I think
that's actually wrong.
That's actually wrong, or maybe the formulation of the question may not be correct here. Possibly you may be referring to a situation where the open loop has unstable poles, but the closed loop is stable, right? So this possibility is there that if the open loop system is unstable, we can make it's stable. But then if you say there is no situation where a system can be stable with even one root on the right half plane. So if you could point to me exact question or an exact example where this ambiguity arises, I will be able to answer that. Where can you get knowledge of electric motor because you are from ECE? Okay, I think
there are courses on
well, I think there is no shortcut answer to this. So okay, I can just ask you to refer to some NPTEL or any of the textbooks on just DC motors. That's what we will be looking at in most of the course. Right? So I think these are there could be some very short kind of lecture contents which will give you a crash course on DC motors. I would really advise you to go through that. I mean, any basic textbook will actually help you that. Or if you want me to post some notes, you can dig out. But again, my sources will be again the same textbooks which are going around. So if you have any particular difficulty in understanding, then I can make you answer that. And all these are again like first order linear systems, right? It's just an RC circuit, so to speak. Okay, so yeah, thanks Amol. Maybe we can take one more question, and if needed, we could meet again next week. We can do it somewhere during the middle of next week. Maybe once in 10 days we could meet up. Maybe you may have a little more questions by the time. Okay, so if there are no more questions, Well, thanks everybody for being here. We'll still keep interacting through the forum, and we'll try to do this live session like about once in 10 days, and I hope that should be useful, right? Okay, thanks everybody, and enjoy the course.